Hello, welcome to today's webinar. Greetings from a sunny and warm Vienna. Uh, so today's webinar is about force measurements for risk assessment. Slides, please. My name is Michael Zillich. I'm CTO and one of the co-founders of Blue Daniel Robotics. So today's webinar is about risk assessment and force measurements and determining speeds. So I won't bore you too long with company details, just a brief background of who we are so that you know who is giving this presentation. So we are the experts in fenceless robotics. How do we do this? We do this with our product Airskin, which you see behind me mounted on the robot. Those white things, that's our Airskin. We are around now for a couple of years, founded 2013 by myself and 3 colleagues from the Vienna University of Technology. We have VC funding since 2018, so we have a strong backer to enable our market expansion. We are located, as I said, in Vienna, where we have the development and also production. And we have around 28 employees now. Briefly about our technology, so that you know what it is that makes the robot stop. Airskin is a soft, pressure-sensitive safety skin for robots and various other tools and machines. The skin consists of a series of individual pads. Each Airskin pad is a soft, airtight hull around a soft support structure. So if the pad is compressed as a result of a collision or being touched, the internal air pressure rises, and this rise in pressure we detect via barometric pressure sensors and safety electronics, and then this issues a safe stop for the robot. As we see on the bottom, if there's no contact, the blue LED will indicate that everything is free. If you press the Airskin pad, the LED goes red, and we know there has been contact. Right, enough of our technology. Here briefly what such a pad looks like. On the bottom left you see the so-called support structure, a support layer made of, in this case, plastic or ABS. On the robot behind me is made of sheet metal. On the support structure we have a couple of mounting magnets which hold the pad. So the pad is clipped on using these mounting magnets, and it's also being contacted by magnetic connectors. And all the pads are connected in series to the connection box you see at the bottom there. So each pad acts as an opening switch in this lane. If one of these pads is then activated, it opens the switch and the safety lines are open, and that's the safety signal then for the robot. So the application we are looking at today is palletizing. I guess you know what palletizing looks like. Let's just quickly do a single run with a single box. You know what the program looks like. So the robot picks up a box using a suction gripper, puts it down on a pallet, and repeats this until the pallet is full. All right. So that's the application we are looking at. What we want to do is the risk assessment for this application. So you see there's no fence behind me. This is a fences application, typically called collaborative application, but really collaboration, strictly speaking, is only one part of a wider spectrum, which you see depicted here. On the far left you have the classic fenced application. The robot is it is in a cage, and its workspace is separated from the workspace of the human. There's no contact allowed, and the robot can work full speed in its cage. On the right you see the various possibilities for fences applications. The classic sort of typical collaborative application on the far right, where human and robot share the same workspace and work on the same workpiece sort of simultaneously. And then you also have cooperation and coexistence. where there's a shared workspace, but that's not being used, for example, at the same time, but only intermittently, once the robot, once the human, or maybe they are not even supposed to work in the same space at the same time, but the human could enter the same space. So that's the important part here. There's always contact allowed in all these cases. It's not required, it's not maybe not even likely or intended, but it's possible. And that's the case. This is what we have to make safe. And what this means is that we will have to adapt the speed to one that is permissible for this specific case. And how to get to that speed, that's the topic of today's webinar. Okay, first we have to start with some norms though. In order to lawfully run your application and adhere to all the safety standards for your workers, you have to follow the machinery directive, which is the EU-wide law concerning worker safety. And there are various national versions of this, and this is the strict law you have to follow. If you do so, and you declare conforming to all the required aspects of this, and then you have the CE labeling for your application. And in order to assess whether you are following this law, you have various ISO norms that guide you through this process. And at the top is the ISO 12100. That's the most general norm concerning safety of machinery. And this also contains how to perform risk assessment. So what you do is, very broadly speaking, there's much more to talk about regarding norms, and there are many more norms you have to follow. I'm just picking out the ones most relevant for today's topic. So you analyze the possible hazards, what could go wrong, what are potentially dangerous situations for your workers, and then you mitigate those hazards with suitable measures to an acceptable remaining risk. And for example, you could change the construction of the application, for example, enlarging distances to reduce clamping hazards, and that's the first step to do, changing the construction if possible. If that's not possible, you will have to use some technical measures. For example, adding sensors to detect the presence of a human or to detect contact between human and robot. And if you use technical measures, then the ISO 13849 becomes relevant. This regulates safety-related parts of control systems, that is safety sensors, and talks about the reliability of these sensors. And for example, if you have a high risk of severe injuries or potentially death, you would require safety sensors with the highest performance level E, which is also the rating that Airskin has. If your application contains robots, you will have to look at robot-specific risks, and these are covered in ISO 10-2018. So here, this mentions robot-specific hazards like, most prominently, an unexpected restart of the robot, so the robot stands still. There's some sensor input from a new box arriving on your slide or something, and suddenly it starts moving. That's a typical risk that you have to look at, and these are listed in this norm. And more specifically, the ISO TS 1566 covers collaborative robots and the risks associated when there's potential contact between human and robot. And this talks about the biomechanical limits, that is permissible forces exerted on human body parts when there's contact. And this is the norm guiding what we do today. And you see there in this dashed line box together, that's because this TS 1566, which at this point is a technical specification, not strictly speaking a norm, but very soon, hopefully, it will be part of the new version of the 10, 2018, hopefully this year, and then this is all part of one package. And what Airskin does is it is a safe sensor with the highest performance level that enables you to build ISO TS 15166 compliant applications. Right. To look a bit into this norm, please go ahead and read it if you want to know the details. Broadly speaking, as I mentioned, it talks about the biomechanical limits for various body regions, pictured in the upper right here. For each body region, there's a specific force value where the typical, the average person reports the onset of pain. So that is what was measured for this norm. For example, for the lower arm or wrist joints, typically at 160 newtons, people start experiencing pain. And that's the threshold you must not exceed at a contact in your application. Since Airskin reacts at 5 newtons, we are way below that value, so we start detecting a contact way before dangerous levels of forces are reached. Also, since this is a soft sensor, it also dampens collisions, thus reducing impact forces. More importantly, and more critically, in most typical applications are pressures. That's the force per area. As you can imagine that a flat area is less problematic than a sharp corner or edge or a needle. And often safety assessment fails, risk mitigation fails at sharp corners and edges. Again, since Airskin covers all the hard parts of the robot or tool and is soft, the contact area is always maximized, and there is never a problem with pressures. So we are today not looking at pressures, but only at forces. Very important for determining the maximum speed for your application is the fact that there are two types of contact situations. There is the transient contact in the free space and the quasi-static contact in clamping situations. You can imagine there's a big difference if the robot hits you in free space and your body can move away, or versus when it's clamped against a fixed obstacle like a wall or some table or fixture. And the transient, the free space situation is much less problematic, and higher speeds are possible. And here the permissible speeds are calculated using an equation in the ISO TS 15166. You enter the robot's mass and the tool and workpiece mass, and then depending on the kinetic energy that the robot stores when moving, and the permissible energy that's transferred to the human body, this equation calculates the permissible speed for a specific body region. For example, 1,300 millimeters per second for the lower arm and wrist joints. In the clamping situation, the robot stopping distance starts playing a very important role. You can imagine if the robot starts stopping, but given the physics of the situation, it can't stop immediately. You would have to travel a couple of millimeters or even centimeters further before it comes to a stop. If this stopping distance is within the compressible, soft compressible distance of the Airskin, it's going to be a soft contact. Once that compressible thickness is used up, it starts becoming a hard contact, and this is where forces then start rising quickly. So this limits then your permissible speed. And in order to find the actual collision forces and thus permissible speeds, you'll have to perform measurements, and this is what we're going to do later on. And then you get to typically much lower speeds than the ones in free space, for example 400 millimeters per second. So it's called a quasi-static contact because it's not entirely static. Here you see the typical evolution of forces in such a contact, in a clamping contact situation. Right after the onset of the contact, there's a peak in contact forces as the sort of robot smashes into the target, and then after a couple of fluctuations, when the elasticity in the robot and also the target, so it gives way a bit, it goes down to a remaining clamping force. That's then the static and constant part. So there's this distinction between the dynamic part of the contact situation and then the static part. And for both of these parts, there are these limits given in the norm. So as I mentioned, the transient contact permissible speeds are calculated using an equation. If you are interested in the details, look it up in the norm. Here just very briefly what it is about. It looks at the transferred energy from the kinetic energy of the robot to the human body or body part, assuming a fully inelastic contact. So the full kinetic energy of the robot is transferred to the human body, and there's a limit for that, for the amount of that energy. And so the kinetic energy is transferred to to the spring energy in the human body, marked in red here. And since Airskin is a soft sensor, it compresses and also stores spring energy, marked in green here. And this is nice because if you look at the bottom part here, the resulting permissible speed following from the equation on top, you will notice that adding this spring energy stored in the soft airskin results in an increased permissible speed, because less energy is stored in the human body because some of it is stored in the soft airskin. So this will give you a higher permissible speed thanks to the softness. If we now look at actual values using that formula, here we have a nice big table. Don't be scared by all the numbers. I'll just quickly guide you through this. So that's the table we use when doing our own calculations. On the top you see the values entered for the application, the robot mass of around 250 kilos for the KUKA Cyberdeck behind me, and then the weight of the payload, 20 kilos in this case, and also the contact area, spring constant, and thickness of the airskin. And then in the table on the bottom you see the various body parts, permissible forces, and resulting from the equation in the colored columns the permissible speeds. And you see for the line, lower arms and wrist joints, the permissible speed would be 1,140 roughly millimeters per second using this in the equation. Adding the term with the softness from the airskin results in an increased permissible speed of 1,300 millimeters per second roughly, which I've mentioned before. That's the part circled in red here. So you get a nice increase in speed just thanks to the softness here. And to demonstrate what these values actually mean, so how do 1,300 millimeters per second feel? I'm going to demonstrate this now using again our demo application. So to see how this actually looks like in real life, I'm going to put myself in harm's way and have the robot collide with me. So this is 1,300 millimeters per second. As you see, it's completely safe, and that's the dynamic part of the application. So now that we have covered the free space parts of the application, let's look at the more problematic, typically clamping situations. Before doing that, we have to make sure that we fully understand the safety settings of the robot controller. And what the safety settings typically provide are uh, safeguarding spaces. You want to have as many safeguarded spaces as possible so that you limit the robot's movement to just the necessary parts. The less it can move, the less it can be, potentially dangerous. Um, and what we have here in the picture on the right, we have these black boxes. These are spaces where the robot is not allowed to go. We see the slide being modeled, then the floor itself, the pallets, the walls, etc. So these are areas that the robot is not allowed to go at all. And this means for most of the potential clamping situations, we can just, remove them by not allowing the robot near enough hard obstacles. Except, of course, where it needs to go, namely picking up and putting down the boxes from the slide or putting down boxes on the pallet. So here we have these blue colored spaces where the speed of the robot is safely monitored, and we run the robot with a reduced speed. So that if there's a clamping, it is going to happen at a reduced speed, and the speed is set such that it is that the resulting contact forces are within the norm. And this is what we have to verify using measurements. So you identify the hazards that are remaining, namely clamping at the pick up and put down location, and for these you define your measurements that you have to take in order to verify that the forces are indeed safe. And we do this using a force measurement device, not just any force sensor. So a simple force torque sensor is not sufficient here. What we want to have is a biophadetic force measurement device, which has human-like characteristics in terms of spring constant and damping characteristics, so that we can properly simulate the respective body part being contacted by the robot. And there are a couple of manufacturers for these devices, for example GTE or Pilz. The device we are using is from GTE, for example, but there are others too. And this is set up for the current spring and damping element are set up for hand and arm. What's important for getting proper, precise, and reliable measurements is to solidly mount the device. You don't want it to move around while doing the measurement, because then you're going to have very jumpy and changing measurements. Also, you have to ensure that this disc that is being contacted is hit sort of vertically and not at an angle, because again this would give false measurements. And of course you will perform a couple of measurements, so if you have outliers, etc., and you're going to take the maximum measurement, maximum value of these measurements to be on the safe side. Also important to keep in mind is that you are not going to measure the current speed in the robot program, because that might change. Robot programs, people might change some aspects of the program, maybe the box dimension changed or something. You have to use those speeds that are the maximum allowable speed within that monitored space you're looking at. So that's the relevant speed. That's the speed that you're going to set as the maximum speed here. Okay, let's now perform some actual measurements. Right. Okay, let's now perform some actual measurements. We're going to hit the device with the sort of most dangerous part of the robot, the corner of the gripper. So we start the measurement here. So the first speed that we use here is 100 millimeters per second. robot is not really fast, it stops. You shouldn't expect any trouble here. Let's look at the results. Here we see the little peak in the beginning, and then it gets flatter in the static part. And we have 54 newtons peak force, and then the static part is 47 newtons. All very safe, far away from the 160 newtons that we are aiming for. I should mention, I forgot to say, this particular clamping situation is actually not occurring in the application because the clamping situation would be the force would be the box moving downward and clamping vertically, not horizontally. But we're doing these measurements to demonstrate collisions in horizontal and vertical direction, just that you have more variation in the cases here. All right, the next measurement is with 150 millimeters per second, a little bit faster. Again, we're doing the measurements here. Let's see. We have 89 Newton peak force and 79 Newton of clamping force, still way below the 160 Newtons limit. All right, next measurement is this one is 230 millimeters per second. Again, a soft stop, and with a peak force of 146 Newton and a clamping force of 134 Newton, which is still below the 160 Newton. So we could actually still go a little bit faster here. So you do this step by step and edge your way towards the permissible force, and then you have your maximum speed that you set within this particular monitored space. Right. So this was looking at the horizontal collisions. So here the gripper comes down vertically and picks up the box. So here the safety spaces are set up such that the robot cannot go near the slide. So it cannot clamp between the slide and the gripper. It can only clamp between the gripper and the somewhat soft cardboard box. So now we're going to put the measurement device on the box. Note that this is not strictly speaking a solid mounting, but this happens to be the collision situation, namely the box being somewhat soft. And so this is, and we want to measure as close as possible to the actual situation that's occurring. So now we're going to put the measurement device on the box. Note that this is not strictly speaking a solid mounting, but this happens to be the collision situation, namely the box being somewhat soft. And so this is, and we want to measure as close as possible to the actual situation that's occurring. So we have 100 millimeters per second downward movement. We're doing the measurement, and you have a peak force of 150 Newton and a clamping force of 95 Newton, which is below our limit. And as you saw, the cardboard box was somewhat dented, which is fine. It's good if the cardboard box is deformed because that takes up some energy, and this helps in this situation. All right, for the next measurement, we're going to use a new cardboard box because the other one is already somewhat dented. For the next measurement now, we have 140 millimeters per second downward movement. Let's see. Doing the measurement, and the peak force is 133 Newton and the clamping force is 105 Newton. So we can still go a bit faster. Again, we change the box to a new one. We are using up quite a few boxes here. And the last test is with 107 millimeters per second. Now the next measurement, and the peak force is 142 newtons, and clamping force is 124 newton. And again, we could even go somewhat faster here. So that's the measurement. So you would normally, again, keep doing this until you reach, and then you have your maximum speed in this area. Now, ideally, you would want to measure the transient contact as well, because the equation that I mentioned that's given in ISO TS 15066 is a very rough estimate. It's a very simplistic model, and it typically overestimates the actual forces. The problem is, though, that there's no accepted and manageable measurement system for doing these dynamic contact measurements. You would need a full, crash test dummy with lots of sensors in it to truthfully measure all the various contacts and the various body positions, and that's not feasible for an actual application. You don't want to measure for days. Luckily, there are current developments where with a movable device, where the measurement device is mounted such that it is moving horizontally, being equipped with different changeable masses for different body regions, and with this you can at least do collisions in a horizontal direction, and that's a good first start. And what we see from these first tests is that the permissible speeds are twice as high from the measurement compared to the equation. So we see how the equation is very, very conservative, and really higher speeds are possible and can also now be validated with such a measurement device. So that's going to be some interesting developments for the future, allowing even higher speeds in fenceless collaborative applications. So summing up, for your fenceless application, forget the 250 millimeters per second, which is sort of a speed that you often hear when hearing about safe speeds. So what this is it's the safe speed for teach-in. So it's a speed which allows a reaction or evasion in time if the worker doing the teach-in detects some problem, but this speed has no relevance at all for collaborative applications, because there the speeds are determined as we just saw. So don't worry, fenced applications don't have to be slow. We saw they can be fast. Forget those 250 millimeters per second. Avoid as many clamping hazards as you can by defining many safeguarded spaces in your robot safety settings. Again, the fewer places the robot can go, the fewer potentially dangerous situations you're going to have. And then for the free space parts of your robot trajectories, you can calculate the permissible speeds. Soon you will be able to measure them as well. And please note that the majority of trajectories are in the free space part, really. And then only for those remaining parts of the trajectories where you have clamping situations, you would have to measure the occurring contact forces and then set the maximum speeds in the safeguarded space accordingly. Why would you want to do all this? Why do you need fenced applications? I guess since you are listening to this seminar, you already have an idea why you want to remove your fences. So speed is mentioned here not because you can go fast without a fence, but you don't necessarily have to go slower if you remove your fence. As we saw, high speeds are possible in the free space parts, so you can continue to have high throughput, low cycle times, also without a safeguarding fence. You gain flexibility. Removing the fence means you can more easily move your application from one place to another. The safety technology, the Airskin goes with the robot. It's mounted directly on the robot. Um, you don't have to move the whole fence, laser ranger, and whatnot. You gain, of course, a lot of space by removing the fence. Your floor space is used more productively. You can put more robots in the same space, more machines in the same space by getting rid of your fences. And of course, in none of this you sacrifice any safety. You are as safe as with a fence, thanks to the high safety rating of performance level E. Right. So that's my part for today. Showing the measurements, talking a bit about the theory behind it, and now I'm happy to take your questions. So the question here is related to AGVs and the permissible speeds from the 1566 for the leg area is very low, sort of uninterestingly low for an AGV. So that's true. The thing is, robots, so AGVs typically have a laser ranger for navigation and obstacle detection and avoidance. So for these robots, the primary technique for obstacles is the laser ranger, and most actually just use a laser ranger, two of them, to safely navigate. But since the laser ranger only looks in one plane, it might miss targets, might miss obstacles that are protruding from a table or a cable hanging down or something, and they might miss obstacles that are at a different height. And these are remaining risks that could be covered with the Airskin. And ideally you would have the laser ranger slowing down the robot when it comes near an obstacle, and then the Airskin covers the remaining risk if the laser ranger doesn't see an obstacle at close range. And it's always a good idea to combine safety techniques for specific situations. Typically there's not one silver bullet that solves all your problems, but you take a combination of different techniques. There was a question regarding this Excel sheet that I showed. It is not downloadable at the moment, it's just used internally, but we'll put a version of this on the website in the near future, so that when you want to quickly find out what are permissible speeds for your application, you enter your values here and get an answer quickly. So this will be put on the website in the future. Then there's a question regarding how does this compare to joint force measurements. That's a good question. So force measurements in the robot's joints are the typical way to for most cobots to determine collision forces, and this really only works well for contact at or near the TCP, the tool center point. So there you get quite accurate measurements, but if the contact is somewhere near the shoulder joint or elbow joint, then these estimates are not quite correct, and you could get potentially much higher clamping forces near the elbow or shoulder part of the robot. And Airskin here has the advantage that it has the same sensitivity anywhere on the surface. It's always 5 newtons roughly. It doesn't matter where the robot is contacted. So that's a clear advantage here in these cases. You have safety for the complete robot, including the tool also. Also, by using the joint force sensors, the robot reacts when the limit force is reached, say 140 Newton or so, that are set in the safety settings. So only when the forces measured from the joint sensors exceeds this, the robot stops or starts stopping, but at this point it's actually already too late. The maximum force is already reached. And then adding the robot stopping distance, you can quickly get over the permissible force. since we react early at 5 newtons plus have the cushioning airskin, we can typically reduce contact forces compared to using joint force sensors. All right, since there are no more questions, thanks a lot for your attention. If you have any further questions that come up later, please just drop us a note. You have the contact, and I hope to see you around next time. Goodbye from Vienna. Cheers.